So let's see. Maybe start a screen somewhere, something. Um, no, it's not. Share whiteboard. Oops. Hey, what's going on? Let's see. Okay. So let's see. Okay, so I guess before I get started, as I mentioned, I'm going to start with new things, but I guess some of you guys are concerned with your midterm and so on, so don't worry too much about that. It's only 20%, and you know that like the spread there is we have quite a bit of spread in your points there for the midterm, but it's more or less like 20 points or something like out of 40. So if you think of that, it's exactly 10% of the overall grade. So it's like actually one grade is like it will get you from A to B or B to A or like B to C or something like that. And given that we have lots of extra credit, including like class participation, actually, I don't anticipate you guys, at least most of you guys, unless you give it up, basically, you'll get a C or below. So you don't need to worry too much about your grade, but I mean, in terms of like if you're not doing too well, like in the midterm, like you probably if you really want to get an A, I guess you can still manage that. Like you just need to seize all the opportunities of those extra credits. Um, but I guess you see like a grade really strictly for the midterm, and I guess there's a reason for that. Like I can't like answer to some of you guys. Uh, some of you guys I asked me personally, but basically the rationale there is it's not just an open book test, it's really an open world test. You can search the internet for the 3 hours, so you can essentially copy everything that I cannot really forbid you. Of course, plagiarism is really a crime in academia, but I I'm not a kind of like God and somehow can figure that out, like whether you plagiarize anything. But if you plagiarized and it's apparently you're plagiarizing, then of course I will penalize you very harshly. Um, and one sign of plagiarizing, or like I shouldn't use the strong word plagiarizing. Hi, can you hear me? But in the sense that you copy without much understanding, or say like, or you just get some part. Say apparently when you're writing something like you don't know what's going on. For example, like you can see in question 4, I I'm quite strict in the sense like for example, like I didn't say explicitly, actually that's intentional. Uh, part A is essentially asking you to prove Fanel's inequality, and part B is use Fanel's inequality to show the converse proof of source coding theorem. So of course, I for the course and also the slides, I show like the converse theorem for like channel coding, and also like source coding with site information. Both of them use Fanel. So essentially very similar. But if you copy that, then of course I won't give you point for that. Yeah, so whenever I see you guys, like for example, change the setup or suddenly become a channel coding problem, or like you suddenly add the site information, that's a sign that you don't actually understand what you're doing, then I'm sorry, like I really cannot give you a point for that. Or like in some cases, like some of you guys actually showing part B in part A, because part A is really asking you to show Fanel, but actually you are actually using Fano in part A, and to prove actually the source coding theorem, then also is a sign that you don't actually know what you're doing. So again, I cannot really give you any points for that. So because this is not even a closed book test. If I close book test, maybe I can give you some point, like just show some sign that okay, you are able to memorize something. Of course, I don't want to kind of like encourage you guys just do word memorization, but here like because you really um, can get any source like to get anything. So I was pretty strict on that. And another way you can think of that is I really grade you or like assess you in the sense you can think of like um, you're submitting something to a conference or journal uh, article. So and in that sense, like it's very important that like what you write is relevant and actually apparently I shouldn't say like it's hard to show that you are correct if you actually try to do some research and have written some paper. Like for most reviewers, it's very difficult to realize if you did everything correctly. If you don't say, right? I mean, like in terms of experiment, no one can verify everything. But if something is apparently wrong, then your paper definitely got rejected. So my rule of thumb will be similar. It's like basically you if you're doing is apparently wrong or like apparently you don't know what you're doing, then I will give you 0 point there. So that's what I mean. Like it's when I guess like this midterm is very similar to experience if you're trying to submit something to journal or conference. If you show sign that you lack understanding, then the reviewers are very harsh on that. Like they won't give you a chance. Basically saying, oh yeah, yeah. No, they will just say, yeah, you apparently the authors don't know what they're doing, and this paper therefore I cannot recommend for publication and so on. Yeah. So and any other questions about the but by the way, I still want to talk a little bit about the midterm because some of you like uh especially I expect like question form may be tricky, even though I think I gave some tips earlier that it may appear in the midterm. But uh anyway, like at least some of you I get figure it out. But I was quite surprised that like I will talk about that more later on. But question one, I didn't expect that like so many of you guys have trouble. So maybe I will repeat a little bit like on question one. And I think like that is actually very important. Also, like if you think of that, like again, like this midterm probably will just like shift your grade from A to B or like B to A or something, whatever. But I think it's a fair assessment because especially for question one, I didn't expect that stumble like so many of you guys, but if you got stumbled by question one, then most likely, uh, actually very reasonably, I shouldn't give you an A, at least at this moment. If I am going to like um, grade you at this particular moment, I really shouldn't give you an A, like if you got stumbled by question one, because um, then if you taken a course with a title somewhere, say information theory, and you cannot reasonably, comfortably compute some kind of like information measures in a rather simple setup, then or you make some apparent mistakes doing that, then um, it's a sign that like you don't really know the materials, right? So therefore, like again, like for that part, I'm pretty harsh in the sense that whenever you write something is apparently you don't know what's going on, then I will give you 0 marks there. So okay, I guess let's see. Uh, and by the way, like as I said, like you guys still have chance to catch up. So I will still give one more homework assignment. I guess I may give it today or tomorrow. So with I'm thinking I would put some extra credit like similar to question one as well. So I would like to make sure if you um you eventually make it up to get an A, you really know how to do question one. So otherwise, I would be really uncomfortable about having you got the A, eventually get the A eventually. So and in that extra credit also I will be pretty harsh. Like if you apparently you still don't know what you're doing, and I will definitely not give you points there. And also you should do it by your own. Like you shouldn't try to, I mean, you can kind of discuss with each other, but you should work out on your own. I really want to make sure you know how to do those things. Like that's very important. Like question one, you can see like it's pretty. I guess that's part of my fault that I maybe didn't emphasize enough for that. I thought like it's apparent like this information is really important. So but anyway, so okay, and also like I guess like about some sign that is apparently wrong. I guess maybe also maybe I didn't emphasize enough. For example, like we have this classic uh inequality. If you remember, if I have like some random variable x, and you can see my screen, right? Let's see. If I have like some random variable x, and I want to compute its entropy, let's say hx, right? Then hx will be bounded by the log of the alphabet size of that x, right? So that's very reasonable. For example, if x is a dice, it's like, or like I should say, x is outcome of a dice. And if you give me result like hx is larger than 3 bits, then I immediately know that something is wrong, right? Because uh, that's only kind of like 6 outcome. Like I know log 6 will be less than log a, actually less than log a, will be less than like, okay, will be equal to 3, right? So I think this kind of stuff, like you should keep that in mind always. Because I see like apparently also if you y is like is binary, uh apparently you cannot have hy is bigger than 1, right? If you have something like that, apparently something is wrong, and you should be able to catch that right away. uh that's also things that, for example, if you write a paper and you do all this derivation and whatever, and y is binary, then you eventually you get a numerical value saying y is 1.45. Then I guess like the reviewer doesn't need to do anything, right? We just say, okay, this paper is rejected because it doesn't make any sense. I don't even need to go into detail for that. So does it make sense, right? So I guess that is help because you guys are graduate student, right? Eventually you are trying to publish, you're trying to whatever send your submission to conferences, journals. I guess one thing really important is that no reviewers is able to spot a paper is absolutely correct right away, but they can absolutely able to catch something is wrong apparently. And when they see something is wrong apparently, um, they won't sympathize you in any way. So I guess that's clear. So this is kind of important. Let's see what else. Let me pull out some of the mistakes you guys made. Uh, and also like this kind of is something of like that is extremely apparent also, right? hxy is bigger than hx. So I think like in one of the question, I guess I asked hy1 and then I asked hy1 y2, something like that. I forgot. And then like if you get the solution that like this one is smaller than this, then apparently you also know that something is wrong, right? Then yeah, then you should do something about that. Yeah. And also let's see. I think I spot at least one case, and also like if your symbol itself it doesn't make sense. Also, this typo is kind of okay, but it's consistently. For example, like if people consistently write IXY like throughout its manuscript, then again like I know that at least okay if he's not submitting to information theory. I mean like for example like transaction information theory, it may be okay. But if it's submitting something is heavily, the manuscript is heavily on information theory, then also it's a sign that he probably don't know the convention well. So you should have a semicolon if instead of like comma here, because like if you have a comma, you cannot distinguish. Like how about if you have X, Y, and Z? This is like, this is not clear. What do you mean by that? So so probably, do we mean by this like the mutual information between X, Y, and Z, or like mutual information between X and Y, Z? So therefore, like the semicolon is like in mutual information is very important. So again, like you don't want to mess that up. And also, like I see, like at least some of you guys did something like that. Like invent something that does not exist. For example, like this. So this does not exist. At least like if you write something like that, you can, okay, in a paper or something, you definitely can invent your own notation or something. But typically, it's heavily discourage you to do that, because like you basically, first you are going to confuse many readers about that. Yeah, I guess that's the most important. Oh, yeah, you're going to kind of confuse many readers about that. And secondly, like most likely you already have like convention like that, or like notations can represent the same thing. People will strongly criticize why you are not using notation that everyone else is using. You just create some of your own that like most likely you also like do not really have knowledge in that field. Like, so showing that like your lack of knowledge. So this does not exist. We don't have something like that. Like we don't have like X conditional Y and conditional C doesn't have something like that. You can say something like, what's the the conditional entropy given you have both Y and Z, or you can ask something like, what's X and Y the conditional entropy given just Z, for example, like that. But notation like this or like that, so this or that does not exist. So again, like, if you write something in a paper, people will just reject it, right? Unless then you explain like why you introduce this notation and what's this notation actually meant for, and so on and so forth. And so let me, okay, I'm not a very organized person, I guess, by the time you know very well. So and also like there's errors that appear in several of you guys. Several of you write something like that. Like for example, like, okay, it's in the first question again. I've something like you say h the entropy of X is equal to sum of, okay, again, like if you write something like that, like this is wrong in many different ways. It also like this, okay, this is self-subject to interpretation. So when I say X equal to A, if I look at this literally, then you say like, when X is determined, okay, it's now deterministic, it's set to be A, and what is the information of that X now? Then of course it will be just equal to 0, eh? Then of course like this doesn't make any sense. The right hand side is all zeros and the left hand side is something non-zero, non-zero, and of course you can say like you interpret another way. You're thinking like this is some kind of instantaneous information, or like I would just precisely define this as like log p x equal to a, or minus log p x equal to a. That's fine, but then like this is also, this equation is not correct, right? The correct equation will be like is equal to probability x equal to a, hx equal to a. But I strongly insist like don't do that. Like unless like when you write this, you clearly explain that like this is defined as this, because I guess it's more common people will think of this is just equal to 0. So, but if you say, okay, actually interpret this as this one here, then this sum should be a weighted sum of like probability x equal to something small x log p x equal to some small x. I have a minus sign here, sum over this x here, and this is basically one of these x equal to a. So again, this is like some kind of stuff like I want to make sure you don't make mistakes on, because like again, like if you have mistakes like this, by the time I gave you an A, I also like feel really uncomfortable that like I really doubt that like I'm making a right decision for doing that. So okay, another thing that also know that like again be very careful. Some of you write something like that hx, or like maybe I use hy here, is equal to h y given x equal to a given a, and then probability x equal to a, or maybe I will just use a summation. Like I use more x here instead. So what's wrong with that? Oh, sorry, this is to be y, of course. Yeah. This, of course, this is wrong because this right hand side is actually equal to hy given x instead, right? But I at least have like a couple of you guys can't afford that like this one is equal to hy, then you start working on things, and of course it will be incorrect. And what else? Let me I have
I had a question for
yes.
this one. So in order for this equation to be correct, there has to be a summation over y as well, right?
Oh, okay. For this one to be correct, let's see. No, you mean this one equal to this one on this side?
Yeah, I mean, for it to be equals to entropy of y, on the right side, there has to be a summation over y as well, right? Different combinations of y.
No, not even that. Like, because you have this hy given x now here. You basically, you can think of like what will be, let's see. Yeah, you cannot actually, because you already have this x here. Of course, you can massage somehow, make it very complicated to get hy, but you don't get hy from here actually, basically.
Okay.
Yeah. So, and let's see what else I have here. And also like I have this one also here, something like equal to sum over hy given x equal to x, some small x. So then of course this is incorrect, because this the correct one should be multiplied by property x equal to x, right? I mean, the way is that you think of that, like this hy given x equal to some small x, it's like if I take that particular small x there, I mean, or like I don't call it small x or something, it'd be easier. Maybe I call it a or whatever, really, I call it a. So is that like hy given x equal to a is saying that, okay, if x is taking value a now, then what will be the remaining information of y, right? Now, hy given x is really think of like the weighted sum of all the different situations. So therefore, like I will have like hy equal x equal to a given x equal to a, and hy given x equal to b, and so on and so forth. But then I need to weight the sum each of other, right? Each of them, right? Because x equal to a only happen with like probability x equal to a. So what I mean is like this, for example, should be equal to just let's say have two values, hy given x equal to small a, probably x equal to small a plus hy given x equal to b, probably x equal to small b, right? So if you skip that, then again it doesn't make sense. So yeah, and yeah, I guess this is the main mistake I saw here in your but make sure like don't make these mistakes, because like this is the mistakes that apparently you don't know the material. And as I said, like if you make a mistake like this in a kind of paper submission in your draft or whatever, then someone will just put a paid course, and that's the end of it. They don't even look at the rest of the materials. Like they immediately say, "Oh yeah, you don't know what you're doing." Yeah. So and any other questions just for these things?
I'm
So
sorry.
yes.
Are you going to question now in class for the midterm exam?
Say that again.
Are you going to treat the correction for the midterm exam currently now? Are you going to give us the
I mean, you
correction?
mean like do we have a makeup test or something? No.
No, are you going to do the correction? Are you going to explain the midterm now?
Oh, do you want me to do that? But I guess I have already given the solution. Actually, I don't want to spend too much time on that. Unless you have a very you don't understand any part, I would suggest you guys just put a question in Discord. So because we don't have too many lectures left, then I don't want to spend all the time just like reviewing the but I just want to pull out this like key mistake like some of you guys make, then want to discuss here. But I won't cover the entire solution again, because if you go through that, really have any things that you don't understand, because by the way, you guys know that the solution is available on Discord, right? So yeah, you probably want to say yes or whatever. Yes. So yeah, if you have if you go through that and have any questions, you and one thing, seriously, very seriously, please make sure you understand question one. Yeah, because I think that is very important, because that's really basic, because then if you don't actually don't understand the solution of question one, then I in the sense I don't think I did I mean like you just wasted I guess like that's the really the take home message of this entire course. Like you should be able to solve problems like question one, similar to question one. So for the rest, I guess like maybe you don't remember like some of the parts, like for example, especially part four, like question four. I'm sure like you may not, if you don't study that after a while, you may not remember that, or that's fine, that's reasonable. But for question one, I think like you guys should have that learn it by heart, or something like you always remember, oh, okay, it's supposed to be computed like that, or something like this, because that's actually very basic. It's like ABC. So and you see a new problems, you know like what was you always know like what's going on, like, and don't make those mistakes I just mentioned.
I
And
have a question. Sorry.
yes, any other?
Yeah, I have a specific question about um, part E of question one.
Actually, is that like about this? I'm going into that.
Okay.
Yeah, I'm going to into that next, because I honestly I didn't think of at all like question one was tricky, but I didn't expect I stumbled the entire class. No one actually answered it correctly. And It was a surprise to me, but at the same time, then I think of that it's probably it's not that surprising. It may be, it's just like the elementary probability class. There's a trap there. Like we very easy to say, okay, we have a con here. Now we it's a bias con. We flip it like many times. Now each time is like independent. Now so therefore it's independent. So I guess yeah, when I make up that question, I didn't think of that was tricky. But then yeah, so I guess let me give another example. Like maybe it's clearer and simpler than the question in the midterm. Like say we only have two cons. Let's say like one con is strongly biased with head, like let's say 0.9 is head, like 0.1 is tail. Let call me this con A here. And then con B is like strongly tail. Right? Now I ask you like if I flip this con 10 times, maybe like five times, maybe 10 times, I don't need that. Maybe 5 times I got head. Now I ask you like, what do you expect the 6 times I flip the coin? Do I get yes? So
can you repeat the question?
I flip like the coin like 5 times already. Now I have 2 coins here, right? But okay, the assumption here is I have 2 coins here, but I don't know which coin I have, right? I don't know. I mean, like basically, I have some bias cons. One is heavily biased to head, one is heavily biased to tail, but I don't know which con I have. But I picked this con like by random. Okay, and I flip it 5 times. I got 5 heads. Now I flip it the 6 times. What do you expect? Like it's more likely to be a head, more likely head, more likely tail, or equally likely. Okay, my handwriting is extremely horrible, but I guess you get it, right? More likely head, more likely tails, or equally likely. So I have this as a question 1. So now all of you get it correctly, basically, right? You don't get it correctly in the midterm, but you get it all correctly. So when you say it's more likely it's head, what does that mean? So I can get it to, okay, get to like, this is like 5 heads, right? How about if I just 1 head? The situation is the same, right? If I flip 1 head now, I flip the coin once and I got a head. So I ask you like, what's the chance you get it a head or tail next time? Is that more likely to be a head, more likely to be a tail, or like equally likely? So wait, why suddenly become tails? First time is a head. Okay. What's the difference about that? Like five case to 1 case? Okay, I will make this question 2 now. It's actually interesting. I didn't expect like you have a different answer. Okay, same question, same answers, but now I only flip 1 head first. Okay, you guys please answer. Put like Q1, Q2. I don't know which one is which now. I got confused. So for question 2, so question 1 is basically I have 5 heads, and then I have this more likely head, like more likely tail, equal likely. Question 2 is I only flip 1 head, but I again like, is it the second head is more likely to be head, or like more likely to be tail, or like equally likely? Yeah, actually, do you guys make up your mind? I mean, remember the setup again is like I don't know which con I have. Yeah. So okay, I didn't say like what was my bias here also, like okay, I would just pick this con like with equal probability. So like probability of like let's say I call this con is like x here, right? And then maybe this outcome is like y1 and y2, let's call it again, right? So then like probability x equal to a is equal to 0.5, and also probability x equal to b is also equal to 0.5. Oh, okay. So let me do it again. Like some of you guys didn't get the question still. So the question is, now I have cons. I have two cons. Maybe one is a red cons. There's A, and then this is a green cons. There's B here, and one is like both of them are biased. Both of them cheated. So one is a heavily head, one is heavily tail. Now I just randomly pick this con like from a jar, and they are not in, they're indistinguishable. I cannot just from their look to know that like which is con A, which is con B. But they just are biased in different way. One is a biased heavily head, one is biased heavily tail. Now, and when I pick from a jar to get this con, of course, I only have two cons there. I choose them equally likely. That's 0.5 chance I get A, 0.5 chance I get B. Now then, now after I pick the cons, I toss it in the first question. I toss it 5 times, and all of that 5 times, I all got heads, all heads. Now my question is like, now I flip it the 6 times. Now I want you to predict what would it be like for the 6 times. Will it be more likely to be head, or more likely to be tail, or like it's equally likely to be head or tail? And now the second question is basically the same, but instead let's say I just pick the coin, I just only toss it once, and I toss it once, I also got a head here. I'm also asked the same question here, like whether it's equally likely, more likely to be head, or more likely to be tail. So you guys are settled. Like, can you just put in your answer now, or like what is it? I guess it's pretty hard to trace back. I will take your final answer as your answer. It's okay, but I will take your second answer. I mean, final answer as your answer, I guess. But yeah, that's great. So if you want to get another put in another answer, it's fine. Yeah. Anyway, I will take your final answer as your I mean. Okay, I guess I'll stop now. Okay, I will wait for one more. Maybe you're still waiting. Okay. So first of all, I think like I guess I would like to convince you. If you pick more likely for head for question 1, you should also pick more likely for head for second question 2 as well. If you pick equally likely for question 1, you should pick equally likely for question 2 as well. There's no good rationale there, like why you pick a different answer, like for this first and second question. I see some of you pick different answer. Actually, wasn't pick different answer. Can you give your rationale there? Like I like to. At least for me, I cannot think of why to think. But maybe you have a reason for that. Like, can you?
Yes, Professor, I think in the first question, uh, we are uh, we get the idea that picking A, like we are mostly picking A instead of B, so which has more head probability. But in the second question, we have only one head, so we don't know picking A and B both are equally as our basic information. So the like the history in A is convincing that maybe next we will have A, but in B we don't have any history. We have only one instance, so we can pick B, we can pick A. In both cases, that is equally likely.
Okay, let me try to convince you. So you have an argument there. It's kind of like, but it's an argument of um it's actually quantity, it's not quality, right? Because like you're right in the sense that for the second case it's less certain, but I'm just saying like which one is more likely, right? So in the second question, you also like already pick head. So if you in the first question you think like, okay, if I take already get 5 heads, so therefore it's very likely to be con A. So therefore like more very likely then the next flip will be like head as well. Then in the second question will be the same, right? But just the degree is less, right? In the sense that, okay, you got an head already. So probably it's a good chance that the con is A as well, right? Then so therefore like it's likely the second flip is also like is also a head. So of course like, if you compute the probability, oh okay, yeah, okay, I'm sorry, like I I I did I confuse you that no, it's not random for each flip. So now so if it's not random for each flip, then you guys are okay, right? So yeah. So basically like for both questions, same setup, just like we always just pick one con from the jar there. And then oh okay, yeah. If you want to make change your solution, that's fine. Yeah. So yeah, for both of them, like you're supposed to just pick one con and then you just flip it like the first case you flip it 6 times and then you observe the first 5 times and then second case you flip it like 2 times, then you have observed the first time. So now okay, then I hope that
Can
like
you explain this again, this experiment, that how we are picking and flipping the coin? Like,
we are just going to pick the con first, right? Randomly
okay.
pick the con first. After you pick the con, you just stay with that con. You're just going to
Oh, we will not pick every time.
no, we are not. Oh, okay. Do you guys have misunderstood like in the midterm as well? Like we are not.
Yes, I think this is the like big
No,
point.
okay, like maybe some of you made mistake because of that, but I'm sorry about that.
Yes,
So, but
yes.
yeah, but
It's like doing experiment from the on every time we are picking and then doing experiment, like picking every time. This is the confusion. Yes.
yeah, no, did the question really say like that? I forgot. But anyway, so let's focus on that. So the setup now is like that. So I don't know how many of you like made mistakes because of that, or like how many of you actually made mistake. So if like that, then I guess it's hopefully then it's obvious that like it's not, therefore your y1 y2 is not independent.
Yes, and that's why I assumed independent even in the mid.
It's not independent, right? Because like you when you flip it first time, you can guess what's the con already. Kind of like give you some information what the con will be. Another option of next flipping implies Towards hat. Oh, okay. I'm not sure. I understand your comment, but anyway. So let's
Uh, yeah, what I actually meant was that since we are flipping it, so once we know that if we pick either of them, it would be biased either towards head or towards tail. So I think that would be another option that because we don't know, we are randomly choosing from A and B, but whatever we choose, absolutely certain that the coin is going to be biased either towards head or tail. So this is something that can be certainly predicted about the next flip, that it's going to be a bias result either towards head towards or towards
when you
tail.
say bias, do you mean bias and drawing the cons?
Yes. So suppose even if I have picked a coin, say B, and I flipped it 5 times and all times it was head. Say all the times it
Actually,
was head, even it was B. But yet I flip for the 6th time, then the 6th time it's a biased chance more towards tilting towards tail and less tilting towards head. Although for the past 5 times it was head, 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 head. Same goes even if I pick A and I flipped it 5 times, and let's say okay it was uh, 5 times head, but yes I flip it 6th time, then it's having more bias towards the head. So this is, I want, if that could be introduced as an option, then I think that would be more. What's your take on that, Doctor?
the bias actually won't really change the situation here. So, but you change the degree. For example, like let's say if I'm more biased toward, for example, like I'm more biased with con B, right? Let's say like if I pick the con B with like probability 0.6 instead of 0.5. Now, but I still got 5 heads there. Then now I should estimate what's the probability I get a head there, right? And I mean, also I should estimate again that what's the probability I actually have picked the con A, right, instead of con B. But if even you are more biased in, I mean, at the beginning, like the probability getting a B is 0.6 instead of 0.5. But if you already get 5 head, then you can compute the probability. Then the probability of getting that is a head. Then okay, by the way, this is actually going to what we want to say about, like, for example, maximum likelihood and map and like Bayesian estimation. So in this case, I can estimate the basically the what is the probability getting an A as a kind of like maximum a posterior probability, a posterior a period probability, right? So basically I can, okay, let me think. So basically probability, let me just use the same color here. Back again. So what's the probability of getting, let's say if I change this to 0.4 and 0.6 here, let's say. Okay. But let's say I already got 5 heads here. So then first the joint probability of getting head maybe like 5 heads and x equal to A will be what? Will be just a probability of like 5 heads given x equal to A multiplied by probability x equal to A, right? Right, so I have like probability of 5 heads given x equal to A, then that will be 0.9 to the 5th, right? And then this will be like multiplied by 0.4, right?
Yes.
Yes. So then I can compute the posterior probability, for example. Actually, I don't even, yeah, let's do that. Let's do that, like compute the posterior probability. So what's the posterior probability? Will be like the probability like x equal to A, given like I have observed 5 heads, right? So that one will be like probability 5 heads x equal to A over probability of 5 heads, right? And of course, I have this one here, right? I have this one here. And what's probability of 5 heads? That will be equal to, maybe I don't write one more, just write here directly. So this will be like marginalizing these two situations, right? It will be like probability 5 heads. Let me just write 5h or something like that. 5h is equal to A, right? Plus probability 5h is equal to B, right? So, and I can compare this probability 5 hat x equal to B, that will be equal to what? Oh, actually, why don't I just stop here? And can you compute this? What's the posterior probability? This is question 3 here.
So I have a question.
Yes.
So how come these 5 heads just a single outcome? Because A and B have a different coins. So if we have 5 heads, then it must be either red or green, right? So then we can see where these 5 heads come from.
Oh, okay. I'm sorry. I mean, wait. This I just put red and green here just for the sake of they are indistinguishable.
So that's my question. How could it be indistinguishable? They have a different.
Oh, okay. How can it's not indistinguishable? You think of like you just have a coin, like just a quarter there. It's loaded, but you just look at that like you cannot see it's loaded or not, right? Or I guess it's more difficult to lower a coin, but maybe you think of a dice is loaded, like it's if you don't have any kind of special instrument to measure that, like that's you cannot tell it. Of course, you can fold it like 100 times or something like that to make estimate like what's the probability to get like 1, 2, or like what's the probability to get a head or tail. But here we assume, okay, we pick this coin, these two coins, just look at that is indistinguishable, right? Then now we are starting tossing them. And we toss it like 5 times, say. Let's don't assume a bias. We assume bias here. Let's say like this is like changed to like 0.6 and 0.4, let's say.
Okay. So A has.
I can even make it quite biased actually.
A has 0.6 and B 0.4, right?
Yeah. So what's the posterior probability? Give me the numerical values. This is quick actually. Like maybe you need the calculator, but this should be quick, right? Oh. So then we have a feeling for that, like. Actually, yeah, okay. Maybe I shouldn't change the value now, but I would say like even you make it pretty strongly biased. For example, this is 0.9 and 0.1. So given that you already got 5 head, most likely that bias is not important. Like you still think that will be a head.
What is the question number 3? Probability of 5 heads given coin is
this one. Yeah. Probably. Yeah. Let me write better. I can remove this now. Actually, I can just say this is question number 3 here. This question number 3 here. So this is I compare this guy. What's the posterior probability? Yeah, let's assume like 0.6 and 0.4 here. So let's stick with 0.6 and 0.4. Yeah, I look at my midterm question again. I think it's quite clear that like you should toss the same coin twice. That's why I say like we toss the coin twice and get the outcomes. So you guys need to read the question and not assume the question like before you're reading that.
Now, Professor, as we get this information today, now it seems clear. Actually, the statement is, because it's open on my screen, so statement is, after picking the coin, and there is, we will toss the coin twice.
Yeah.
Here it is making clear that we will not pick every time. But this was a basic glitch in the whole process. That's why we were making, like I have made the whole tree in this analysis.
Yeah, but yeah, it's interesting though. Like I don't know how as I said, like how many of you because of that to miss it out, and how many of you actually think otherwise. So let's see. So how you guys did? So what the values I have very different values. I guess it's like 0.6 and 0.4, like 0.35.
Is probability of A 0.4 or 0.6?
Yeah, 0.4, 0.6.
Okay. Probability for picking coin A is 0.4 or 0.6?
Oh, sorry, 0.4. Like A is 0.4.
Oh, okay. I did a mistake.
0.6. Oh, the value is so big. I don't know. Like I trust like so. Let me run it myself. So are you sure? I'm thinking like the value should be like more biased to one side. So you guys done? So
Here we are.
yeah, actually it's conjugate. Yes, I think the value should be very close to 1, actually. When you get 5 heads there. Hey, but you cannot bigger than 1. If you're bigger than 1, again, I don't do this kind of stuff like when you cannot have probability bigger than 1. When you have something bigger than 1, you need to make no, it's not one thing error. It has to be like something's wrong. Yeah. You probably have a sign that you should be plus, and then you change it to minus, something like that, I guess. Yeah, I guess that should be closer, like 0.97, 0.98 or something like that. But Kantian's solution basically is correct, like that equation, right? Like you have you also compute like what's the probability of getting 5 hat, and like x equal to b, that would be just equal to probability 5 hat given x equal to b multiplied by probability x equal to b, right? And this is 0.6, this is 0.1 to the fifth, right? So this value should be much smaller than this one. And when I compute this guy, the posterior probability is just equal to probability x equal hat, x equal to a 5 hat over probability x equal to a 5 hats plus probability x equal to b 5 hats, right? And yeah, I think that is like 0.9. I don't know how big. Yeah, actually it's 0.99 something, right? So okay. Anyway, so it's like this would be 0.9 to the fifth, 0.4 over 0.9 to the fifth. Oops. Oops, I cannot undo. I'm trying to press the keyboard to undo. It's crazy. 0.9 to the fifth, 0.4 plus 0.1 to the fifth, 0.6. Yeah, something like that. So I guess it's like 0.99 something. Yeah, it should be pretty steep. So actually, you can vary that yourself, right? You can make it more biased. Maybe you can make 90% biased. But if you go to get 5 hats, chances like that one is very likely to be con A. And of course, if you are not that extreme, maybe you get like 3 head and like 2 tails, then like it's harder to say like which is which, right? So I hope that's clear. So this is like very straightforward. Right? I guess like for you guys, didn't heard of that before. Probably you do. Like this is just this MAP, right? This maximum a posterior probability a posterior. So we're trying to maximize the a posterior probability. So in the sentence, we are trying to estimate this x. Estimate which con we pick, right? I guess it's a maximum a posteriori or something like that. Yeah, yeah, because you have the cons itself, like it's so likely to be head, and another one is so likely to be tail, and when you get like okay, why not give one more quick exercise? I just make sure you guys got it. And also for situation 2, like I only get 1 head, right? Probability x equal to a, just given 1 head. So let's again, I just use 0.4 and 0.6 here for the bias. Yeah, that should be pretty simple, right? So I guess yeah. But you see that like even I'm slightly biased, and I got even 1 head there. It's actually we are quite certain like that con is a head. Like it's a sorry, I mean the con is con A already. It's like biased towards head already. So therefore, the second time I flip it, already is a good chance that like this is going to be a head as well. Yeah, yes, because like these 2 cons, because they are so biased themselves. Like one is so biased to head, so the other one is so biased towards tail. No, I guess I would just use this example to explain maximum likelihood, maximum a posteriori, probability, and also Bayesian. So now, if
I had a question.
Yes.
Okay, so about the question, sorry, part D, I think. Let me check just a second. So in part D, we were asked to sorry, part E. We were asked to find the mutual information between the first coin flip and the second coin flip.
Yes.
So my assumption was that I mean, the two coin flips are independent of each other because the first coin flip does not affect the heads or tails probability of the second coin flip. So does this the proof that you just gave, that the probability of a given single head, does this prove that they are not independent?
Yes, actually, that already show that when you because if they okay, basically if they are independent, then if they're independent, from my results there, okay, basically I should not get any information. That should be equal to 0.5. Of course, this is not equal to 0.5, but I'm saying like if they are independent, meaning that like the first time I got something like from, let's say this is Y1 here. I don't call it, I just use the same name like as. So Y1 is like, is whether it's head or tail, it's not going to help me to estimate what the con currently is. So therefore, I cannot tell. Oh, I cannot tell like what's the next flip. Yeah, I'm sorry. Like I'm thinking like I'm just make you more confused. I saying it this way. So maybe like it will become more clear when you play a little bit more on the numbers. But the high level idea is basically you think of like when you don't know which con you are picking, then it doesn't matter whether they are independent or not, right? If you know which con you're picking, so if you know like you are having con A, then each time you flip it is indeed independent, right? So
Yes.
in the sense like the second time you flip it, the probability. So when we say independent, it means that like probability, let's say Y2 equal to head, given Y1 equal to head, will be just equal to probability Y2 equal to head, given Y1 equal to tail, right? So it's not going to change your estimate of your probability next time, no matter what you have earlier for the first flip. And this is indeed the case, right? If I know this is con A, then no matter whether like at first time I flip a con is like equal to head or equal to tail, I will still have like probability Y2 equal to head is equal to 0.9, right? But on the other hand, if I don't know this is con A, I have no idea whether it's con A or con B, then apparently you get a very different results, right? Okay, I haven't estimated this yet. Actually, I'm going to ask you to estimate this. This is actually the Bayesian estimation. I'm jumping ahead. Really. But let me maybe I don't know, maybe I use a clean page is better. So I map maximum likelihood and Bayesian estimate. So now I use my same example here. And okay, let me make it less, okay, please don't mind I change the value a little bit just for because for the sake of explanation here, so so I will have con A. I changed the value now. Please forgive me for that. Instead of like 0.9 and 0.1, I would just say it's bias 0.6, like head is 0.6 and tail is 0.4, let's say. This is con A. And con B, that's basically like the other way around, 0.4 head and 0.6 tail. So now, but I changed the bias a little bit. Let's say I somehow, for some particular reason, maybe I have a jar that I have a 3 con A, maybe I have a jar there, right? There's like 2 con A's there and 1 con B there. So now therefore like I have a better chance to get a con A, right? So I have 2/3 of a chance to get a con A and 1/3 of chance get a con B there. Now let's say I also like do a flip, like, but this time let's say I also like the same setup. I pick a con here, pick 1 con here. I'm just flip it twice. But this time, let's say the first outcome is tail, like all of this is tail here. Now I'm going to predict the second toss here. I want to know what is this now. So the Bayesian will be just the most direct one. I will basically compare what's the probability of Y2 is, let's say, head, given Y1 is equal to tail. That's basically the Bayesian way to do things. So for map or maximum likelihood, what we are going to do is I'm going to first estimate which con is likely to be first. So let's say I'm trying to maximize the probability that X is equal to something, a con, right? Given Y1 equal to tail, I maximize this. See here, that can be con A or con B. And after I maximize that, then then I would just assume, okay, therefore like that's high posterior probability to be like con A or like con B. So then I will estimate the probability of that Y2 will be just equal to probability of Y2 given I have the con is equal to that optimum con or the con that I estimated. And maximum likelihood is very similar, but I just ignore the prior basically. I assume I don't know the prior. So therefore, instead of maximizing the a posterior probability, I'm going to maximize just the likelihood. That would be like the probability of Y1 given the observation. This is basically the observation. And I have like I'm trying to estimate the parameter. In this case, the parameter is whether it's con A or con B. So C will be A and B. So such that like, again, I'm doing the same thing. Like my probability of Y2 will be just estimate of pi 2 given X equal to C. So is that clear? Okay, I don't know whether this is question what? Let me take it back. Let's see. This is question 5, maybe. Like, I guess I would do it like one. I mean, so question 5 like have 2 parts like together. So what is like probability of Y2 based on like maximum likelihood, or probability of Y2 based on like map? Is that clear? Like, what does maximum likelihood and like map? Okay, let me let me repeat again. Yes, let me repeat again. So, but let's see, the setup, is that clear? The setup, is that clear? The new setup, is that clear? I have the setup very similar to to previously, but I changed the values a little bit. Now, con A is only biased to 0.4 to head for head, and then con B is like biased 0.6. Oh, sorry, not 0.4, 0.6 for head, and then con B is only biased like 0.6 for tail. And then the chance of getting a con A is 2/3, and the chance of getting con B is 1/3. Now, I mean, like maximum likelihood and map, they both have a similar rationale. So if I ask you to estimate, okay, the final goal here, let me repeat the goal here. The goal here is, okay, what's given here? Given is like y1 is equal to tail. So we flip the con once now, and we got tail. Now the goal is I want to estimate what is y2 is equal to head or tail. So of course, if I know y2 equal to tail, the probability, then I know what was y2 equal to head. But either way, so I want to know what's the probability of y2. What's the probability of the second flip here? So
Probability of y2 or probability of y2 equals to head?
it's the same thing, right? I want to know the distribution.
Right. Yes.
Yeah. If I know y2 equal to head, yeah, you're right. Maybe I let me be specific for the question, because if I ask you in the question, let's put it this, like y2 equal to head. Yeah, sorry about that. Like, yeah, yes. I want to know what's the y2 equal to head, but that's the goal, right? So that's the goal. Is that clear? That's all. I'm given that I have the goal here. Now I explain what's the difference about like map, maximum likelihood, and Bayesian now. So for both map and mass, actually Bayesian is most direct, or like you can think of like most reasonable. Well, I just directly compute that. So given y1 equal to tail, what's the probability of y2 given head? Right, this is what you given. What's that things I try to compute? Okay, I just try to compute this directly. Maybe I will put it question 6 for this Bayesian. For Bayesian. And for map, maximum likelihood is a little bit indirect. What we're going to do is we think of the con itself as like a parameter. So we don't know what's the con supposed to be, right? What we're trying to do is we first trying to estimate what con it is. So let's say like we are going to estimate in terms of map, then the way will be very simple. I will just look at like what is the posterior probability of like x equal to c given y1 equal to tail, then we see which one is bigger, right? And then wait a sec, maybe I write it this way. Yeah, sorry, maybe I write it this way, is clearer. The optimum con will be, I put c hat here. Is that clearer? So basically I'm trying to maximize this posterior probability, right? This is again a very intuitive, right? So given what is given now, the first toss is a tail. Now I'm trying to maximize the probability that the con, what the probability of a given con. So whether like x is equal to a is bigger, then I would pick like the con should be a, right? If x equal to b is bigger, then I pick con as b, right? I pick c hat as b, right? Now after I determine the con, then the probability, my estimated probability here will be simply equal to the conditional probability given that optimum con there. So map and maximum likelihood is very similar. The only difference is that for maximum likelihood, we will just ignore the prior probability completely. Basically, the prior information, I don't care. Assume I don't know the prior information. So therefore, like if I don't know the prior information, I will just, this is known as the likelihood way. I'm just basically like maximize the likelihood. The likelihood will be like, given some parameter, what will be the observation? I was just going to maximize this value here. And then once I maximize this value, I know what parameters maximize that value. Then I will just in this case, the parameter will be just say whether it's con A or con B. then I will just again approximate the probability of y of the second toss as the probability of like tossing that particular coin that we determined. So for example, like if the optimum coin should be A, then my estimate of probability y2 equal to hat just equal to 0.6.
So, Dr. Chang,
Yes.
in this question, we are given that y1 is equal to tail.
Yes, we are given y1 is equal to tail.
Okay, and for maximum likelihood, we are not even going to use that, but for map, we will use that.
No. We would always use the observation. We're just not going to use the prior. This is the prior, right? This is like basically is the probability x equal to A. This is equal to probability x equal to B.
Okay.
Yeah. Yeah, I guess okay, this is a kind of so for those like already kind of done with question 5, you can go ahead with question 6 as well. Like, so what's the Bayesian estimate? So, but we'll kind of take a break. I'm not sure this was supposed to be like so maybe I actually I'm aware I'm just going to feed my cat really. So but maybe kind of like we start like at like kind of like 4:35. My clock here is like 4:23, maybe like 10 minutes or something. So but you guys can work on that. Like, so see if you and let me know if you have any questions as well. Okay, I guess back. So I guess many of you guys are kind of done. So okay. So I still give a little bit more time, or maybe I work a little bit on the Bayesian thing. Then because I didn't work on that myself, so let's see. So I supposed to compute this way. Now let's see. Maybe I use a what here. I know probability y2 equal to head, y1 equal to tail, and x equal to a. Okay, that one is if x equal to a. Let's see. Okay, that let me expand that first. This is a probability x equal to a, and probability x y2. Let me just shortcut y like tail h, like first one is tail, second one is h, and x equal to a. I use a shorthand here. And that will be equal to probability is equal to 6 is 2/3, right? 2/3. And given x is equal to a, then I will have like head and tail is a 0.4 times 0.6. So it's a times 0.4 times 0.6, something like that. And also let me see if like y2 equal to head, y1 equal to tail, x equal to b. That will be equal to px equal to b, p tail head, x equal to b. That's equal to. Oh, by the way, if I made any mistakes, please let me know, because it's definitely very easy to make mistakes. It's like 0.4 times 0.6 also, right? Now then I can sum them together, then will be marginalized, right? So if I sum them together, basically probability of y1 tail y2 head. Let me again use this shorthand notation. Probability h will be just equal to the sum of these. So it will be like 2/3 0.6 0.4 plus 1/3 0.6 0.4. So it's a 0.6 0.4 basically. So it's a 0.24. And I can compute like probability of, let's see. I basically I have what did I compute? I just compute like probability y2 equal to head and y1 equal to tail, right? So if I also compute so I want to compute this guy will be equal to probability y2 equal to head, y1 equal to tail. That I just already compute already. Over probability y1 equal to tail, right? So compute this probability y1 equal to tail. This can be equal to probability of y2 equal to head, y1 equal to tail, plus probability y2 equal to tail, y1 equal to tail. So therefore, the only terms I'm missing is I want to compute this as well. So I can do the same thing here. So to compute this guy here, so I have both of them tail. Let me just again shorthand now. Tail x equal to a, right? Tail x equal to a equal to probability x equal to a, and probability tail given x equal to a. That's equal to probability of a is 2/3. Probability of tail will be 0.4 times 0.4, right? And then probability of tail x equal to b will be probability x equal to b, probability tail x equal to b equal to 1/3 times tail is 0.6 times 0.6. So therefore now I have probability of tail is I just add these two together. So it's a 2/3 0.16 plus 1/3 0.36, right? So I don't know, this is like 0.12, this is like what? 2/3 let's see. This is probably 0.11 something. I don't know. I just approximate 0.11, I guess maybe. And this is a this is 0.12, right? So this is approximately 0.23, something like that, close to that. So then my this value, so therefore it's just equal to, let me rewrite this again. Is equal to P probability, again use the shorthand here, is equal to TH over PTH plus PTT, and my PTH is a 0.24. This is about 0.23, I don't know. So yeah, this is be 0.5 something. So all of you guys get 0.5 something. I guess I need to use a calculator to get exact value here. Maybe let me just bring out Octave or something like that. Let's just wait a sec. Oops. Let's see. So I have like 0.16 over 3 times 2. There's actually 0.10667 because that actually more accurate is 0.2267 or something like that. So therefore this is a 0.2267. So let's see. 0.24 over 0.24 is 0.2667, let's say. So should be 0.14 something, 514. Yeah. So yeah, okay. Some of you guys get the same value. I'm comfortable. Yeah.
Dr. Sam?
Yes.
I have the same answer, but in the denominator, you have probability of tail head plus tail. So I just considered probability y1 is equal to t. And then I just used the Bayes rule I just expanded that.
Oh yeah, it's okay. Yeah, I just do it like the way that I don't know, the one I'm a little bit comfortable. So because I hear like I actually you can do it many ways. So because this is just a probability something like there's many ways to expand that. So Yeah, but I just get used to like just find the joint probability first and then marginalize to get all this. And in particular, the denominator here, yeah. I don't know. It's just that's just how you get used to that, honestly. Yeah. So anyway, so I guess many of you get the same answer as I do. I don't know whether it's I think it's correct. Like usually when several of you guys, several of us get the same values, probably it's correct. So actually for map and maximum likelihood is easier. So let's go to maximum likelihood, for example. So as long as you understand like let me this is let me get some space here. As long as you understand the notation, it should be pretty easy. So we are trying to find the most likely con from our oscillation. I'm ignoring the prior, right? So therefore we just look at given if it's con A, what will be my oscillation, right? Now my oscillation now is like I got a tail. So if it's con A, so therefore I have like probability y1 equal to tail given x equal to A. That value is simply just equal to 0.4, right? And then I have probability y equal to tail, x equal to B. It will be just equal to 0.6, right? Now I pick the one that's most likely, then therefore I will pick this one, right? So therefore my optimum con here, my estimate con here, this C hat here should just equal to B, right? Just equal to con B here, right? So if I assume this is con B, then what is the probability now? Then the probability of getting a tail will be just equal to the probability of y2 given the con is con B, that is a C hat is B here. So that will be simply equal to 0.6, right? Sorry, not 0.6, 0.4. Because I'm asking, let me write clearly. I'm asking the probability of getting a hat. So hat. So this will be equal to 0.4, right? And for map, basically the idea is exactly the same, but we'll take the posterior, take the prior probability into account as well. So then let's consider, so basically we will compare. So first of all, I guess I look at this expression here, this posterior probability here. Typically, we can simplify like that because this will be just equal to the joint probability. Maybe I use a different color again. Maybe blue. Joint probability over probability y1 equal to tail, right? Joint probability give over the observation here, right? That's basically the posterior probability. Now, but we are optimizing what? We are optimizing the parameter, the con here. The denominator doesn't depend on anything with respect to C, right? So therefore, like we can just pull this out, right? So, or like we can just ignore that, or like pull that out. So therefore, like it's the same. The map formulation is the same, even though we're trying to maximize the a posterior probability. It will be the same as maximizing the joint probability. And the joint probability here will be just equal to probability x equal to C multiplied by probability y1 equal to tail given x equal to C. Okay. Now, if you compare with the maximum likelihood, it's essentially the same. The difference is that we just multiply the prior as well. So we'll add the prior as well. So now, therefore, we should compare what? Compare when C is equal to A and C equal to B, and we look at like which one is bigger. So we will basically, let's see what I'm going to do. I guess it's okay. I can erase this part now, right? It's fine, right? I will say like when x equal to A, so A tail given A. So what's that? That would be equal to probability of A is 2/3, right? 2/3. And tail given A is a 0.4. Yeah, it's equal to 0.4. And we want to compare with like when X is equal to B. X is equal to B is the pi probability of B is equal to 1/3 multiplied by probability tail given B. Tail given B will be just 0.6, right? So then we will look at which one is bigger, right? So, and this is what? This is 0.2, right? And this one is, it's basically big, should be bigger than 0.2, right? So it's like 0.4/3 will be bigger than 0.1, right? Multiplied by 2 will be 0.2 something. So this should be, so therefore this one will be bigger than this one, right? So therefore the optimum con now will be equal to A, right? So I should select A. I will estimate, okay, I would guess that like the con I actually use is like con A. So therefore, like if I estimate what's the probability of Lex toss will be simply probability of Y2 given X is equal to A. So X equal to A is just equal to 0.6. So is that clear? I see like yeah, some of you didn't get the right answer for map. And if you get answer like maximum likelihood and map is not equal to 0.4 and 0.6, you have some misunderstanding here. Basically for the map and the maximum likelihood, like we're trying to estimate the con first. We're trying to guess which con we're using first. And then in terms of estimating the probability of Lex toss, then I would just simply use the probability of the con that I think is the actual con. So therefore, in this case, it will be either 0.6 here or like 0.4 here. So any questions or anything unclear? I don't know how many of you kind of see this before. I think like if you did kind of degree like in electrical engineering, you should came across of maximum likelihood and map before, like, yeah. And but maybe it's not. Oh, okay, yeah. But maybe it's not in the sense that like it's actually very common. And for example, like in communication, that's use loss of estimation, like just based on map or like maximum likelihood and so on. And theoretically, like Bayesian is like so the most you can say accurate or something, but it's not always you can compute Bayesian easily. Sometimes it depends. Like, for different problems, maybe you have different situation. You will see more basically. So I guess I will continue to expand this example. So what I'm going to do is now, like if I don't know actually what the initial con I have, I mean like again like this is some kind of bias con. Like I don't know, like my friend like to trick me, like he has this con and he always have this tricky con here, and I have no idea whether how biased it is, like whether it's biased to what yeah. Let's see, you have a question. Can we do it like do you mean by the Bayesian one? Like, but the Bayesian one, you don't get the right solution though. I probably not. I'm not even sure like where do you get that value here. 2/3 you Yeah, can you elaborate? Are you trying to estimate the Bayesian? But anyway, yeah, you cannot get, yeah.
So I'm trying to elaborate the Bayesian. So
Yeah.
basically, if I had at the second toss, then I am basically calculating the whole probability for getting head at the second toss using coin A, and then what's the probability of getting the coin A, add with the probability of getting second time head for coin B, and then the probability of coin B, and adding them together. So is this Bayesian, or what's your take on that?
My take is, yeah, it has to be something wrong, like, because the numerical value is not the same. So after all, ultimately what Bayesian does is very I mean, high level is very intuitive and reasonable. It's just directly estimate the probability there. So for your equation there, I'm not sure where. Yeah, if you just write all these numbers here, I'm not quite. Let's see, 0.6 square.
Yeah, so for coin A, the probability of getting a head is 0.6 square, and for coin A, tail head is 0.4 into 0.6, and then the probability of coin A
So
itself.
what's the first term you are thinking to compare? Can you say, like,
Yes.
precisely what is the probability of the first term there?
Yes, so the overall first term that is being multiplied by 2 by 3, it is the probability of getting head for the second time using coin A.
Wait, yeah.
Probability
Yes,
of
okay.
getting head for the second toss using coin A.
Actually, like, for one thing, I don't see like how this value can be a conditional probability, because you are doing is summing and product, right? So when you let me erase. Oh, okay. Let me just write on news something. So so when you sum and product, for example, you start with some joint probability here, anything like x, y, z, right? It can be like written as I am product of something, right? So you multiply them together, and if when I marginalize, then I will add them together, right? For example, I can have like xy is equal to xy z plus z1 p x y z2, right? So you look like you have a form like that. So if you are doing something like that, all you get is always a marginal probability, right? So if you're trying to guess a conditional probability somehow, you have to have a numerator denominator, right? Somehow I don't see you have a denominator here. So that I think, yeah. But I think it's a numerical thing. So you need to I don't know, I shouldn't say numerical thing, but it's an algebra thing. Like you just keep using base rule. Like that's nothing magical about that. Basically, just playing with like algebra. But here, like I'm pretty suspicious, because what we're trying to do is get this conditional probability, right? A conditional such that like y2 is a head and y1 is equal to tail. So somehow you should have something like that, right?
Okay, let me maybe reevaluate it.
And the denominator is not showing somehow. Yeah, but anyway, I'm so sorry. Like maybe like we should continue first. Yeah, if you still can figure that out or something, like we can discuss offline, or like you can put it on Discord maybe. Yeah. So okay, let me let me continue with this example first. So, so as I said, like, let's say I don't even know if there's I start with 2 coins to start with. I don't know, like, again, I have a jar, right? I pick a coin there, right? And I don't know how it's going to be biased. It can bias in any different way. Like, again, I can either head or tail, but I don't know what's this probability of head and tail, basically. But it can be biased, it can be fair, but I don't know. It can be biased more towards head, it can be biased more towards tail. And I asked same question, basically. So if I flip the coin like 1 times or 2 times, and now I want to continue to flip it, and I want to predict the probability of next flip. Then how do we do that? So first of all, if basically if we are doing maximum likelihood, then we are essentially ignoring the prior, right? Then
I have a question. What do you mean by ignoring the prior? Can you clarify that?
Ignoring the prior is like, okay, and let me go back to look. Maybe here is still not clear. Let me go back a little bit here. Oops. So for this one, originally, the maximum posterior is like maybe I make it like easier to read here. So this is a basically map is like you have some observation. In that case, observation is like whether head or tail. Then I'm trying to maximize this parameter here, this C here. This is a parameter. And I want to find the probability. That's very reasonable, right? I mean, like I have this observation now. Given the observation, each parameter have different probability, right? Have different chance. Then I will just pick the one that's most likely, right? But for the maximum likelihood, I'm doing the opposite. Actually, I also I want to elaborate here again. I did, but let me elaborate this again. This is actually proportional to PC observation, like the joint probability, and is equal to PC multiplied by P observation, given the parameter here. So therefore, if you think of like this interpretation here, let me write also maximum likelihood. Maximum likelihood is just like that. So it's just like that. So the difference of map and maximum likelihood is just like for map, you scale your likelihood with the prior probability here that you believe like what is the bias of your parameters, and you put it into as a bias. And for maximum likelihood, you don't have that. Basically, you just completely just look at the observation and trying to find the parameters give you the maximum likelihood. So is that clear right now?
Yes.
Okay. So then if we think of the maximum likelihood, it's like we don't care about this, and for this one, given the observation here, we want to maximize the most likely what will be the combination of of course, in this case, I have A and B here, right? But I have for here, right? I know it's a con A or con B. But now in this case, if I don't know like what kind of con I have at all, then it can have different kind of bias, right? You have completely different bias. Like you can have like maybe like 0.9 is head as we have at the beginning, or like 0.9 as tail, or like even like the con is so crazy, it's like always give me head or something like that, right? So then in that case, if I have like my oscillation, let's say I also like have 5 hats, let's say, and I trying to, this is my observation here, and I'm trying to estimate this parameter, my parameter, let me call it Q here. Q is equal to probability of hat to optimize this. So I'm trying to maximize this to find the optimum probability there, right? Maybe less extreme. I have like 4 hats and then 1 tail. Okay, I don't know. This is question 7 or something. So what was Q hat in this case? Is that clear? Like what we're trying to do? Now the problem is that we relax quite a bit. Now we don't know, we don't have any constraint on the con. Yeah, we don't have any constraint on, in the sense that I have the draw, I have no information now. I don't know there's a con A and con B. Con A is biased like 0.6 to be a head and con B is biased like 0.6 to be a tail. Now I have absolutely no information at all. I just pull out a con. Now the con can have like really bias, for example, like it can have like this probability of hat is equal to Q can be like maybe 0.99 or whatever. I don't know. But based on a maximum likelihood estimate, if I try to estimate the con, how biased or like what was the probability of like getting a hat for that con, it's very simple. Basically, I'm just trying to maximize the likelihood. That's basically given some parameter Q here, or I assume the con have the probability of hat is exactly Q here. And then like from that, I can have the probability, the corresponding probability of like getting this observation, like 4 hat and 1 tail, right? For different Q, I can have different probability here. Now I'm just trying to maximize this Q here. I'm trying to find the probability of hat that maximize my observation. For example, like let's say I give more precisely, let's say Q, if like for Q is like 0.3, then given my observation here, then my probability, this probability value will be just equal to 0.3 to the 4th and 0.7, right? Times 0.7, right? And if my Q is equal to 0.6, then I will have 0.6 to the 4th and 0.4, right? Something like that, right? Wow, you're so quick. Are you sure? So now I'm trying to find that one to maximize find a Q that actually will maximize my conditional probability here. By the way, this is a calculus problem, right? You know that, then you can basically you need to figure out what's the random variable. Actually, I can basically this Q is the random variable, right? This not the random. I'm sorry. Q is a variable, right? A parameter you want to find, right? And then oh, that's 4 hats. Yeah, 4 hats actually. But you're right. Counting you're right. But that's 4 hats. So therefore you should modify your value a little bit. So do you want me to give you some time to, or like should I move on? Yeah, and yeah. Maybe I'll give you a minute to digest, for everyone to digest. Yeah. Yeah, I guess everyone got that. So you see that like we basically have the parameters like this q here, right? So we have q to the fourth, right? And then like 1 minus q here. So this is like the likelihood. So I want to maximize for q here, right? I try to maximize this q. Then we will what take derivative and so on, right? So now the parameter is q here. So if I take derivative, it's like 4q cube. Hopefully I didn't make mistake here. Plus take this one is like -1, right? Times q to the fourth, right? Okay, something like that. So I was just take it to 0. So I get what? So I will get like q third for 1 minus q here equal to 0. Wait, I think I probably have made mistake here. Yeah. You guys kindly, okay, that's, I miss, wait a sec. After a while, you don't even know how to take derivative. Let's see. Did I make anything wrong about that? So I'm trying to maximize this guy, right? So I assume I can just take derivative, right? 4q third 1 minus q, right? Q fourth, take this one -1. Yeah, it looks good to me. So minus q minus q. It looks suspicious. I have -2q here, 4 minus 2q. I have q equal to 2. Oh, okay, of course I cannot have q equal to 2, right? 4 minus 4q. Oh, yeah. That's so stupid. Yeah, thank you. Yeah. It's like, as I said, like, cannot do algebra now. So it's like 4 minus 5q. Yeah, that's good. So then therefore, like the optimum q is set to 0, q will be like just equal to 0.8. Yeah. So thank you for pointing that out. So that's maximum likelihood. But then as you can see, this estimate is quite extreme, right? So for example, like if I have maybe just 3 heads here, if I toss like 3 times, I got 3 heads, then I'll just say, oh, okay, I predict the next time will be definitely head, because I think that like my con will be like basically like the probability getting a head is 1. So of course you can fix that. You can put in a bias there. Then if you pick a bias, so then in that sense, like, okay, let's work on that. So let's see. If let's get back to like 4 head and 1 tail or whatever. So if I do map, so what I'm going to do is say, okay, I have some q parameter q here, right? So I have this p here is basically q to the fourth and 1 minus q to the just 1. Now this is this guy. Now I want to add a pair here also, probability q, right? That's my pair. Now the thing is that you can insert any pair here, but for convenience, so this is the concept of conjugate pair. For convenience, so of course I want to pick a pair that have the same form as the likelihood, right? If it has the same form as that, then basically my computation will be simple, right? Much simpler, right? So each time I just multiply this pi, it doesn't change the form. It will be just basically the same form. I try to maximize the likelihood is essentially the same as the computation to maximize the a posterior probability will be the same as maximizing the likelihood. So I want to conjugate pi is basically try to make it same form as the likelihood. So we pick a pi such that it's a same form as the likelihood. So in this case, what should I pick? It's in your homework assignment. Do you remember? So basically, we want to pick something like have this form, right? So I want to pick a pi like q to the a and 1 minus q to b. Actually, by convention, will be a minus 1 and b minus 1, I think. If I have a form like that, of course, like this thing is, if it's a probability, like if I just have this thing, it won't be kind of normalized, right? So I want to make sure this guy will be normalized if I take the integration, integrate from like 0 to 1, right? Because Q will be like probability, right? Q is like probability of hat, right? So it can only take a minimum of 0 and maximum of 1. So if I take this, integrate, I mean, if I integrate this guy, I hopefully I should get a 1. I need a normalization factor here. So anyone remember the normalization factor here? Yeah, this is the beta function. Yeah. Let me get back my slides. Where's my slides? Let's see. Just want to make sure I don't make mistakes. So yeah, actually this normalization factor is just this beta thing like BAB. If you remember in the homework assignment, this BAB is equal to gamma A, gamma B over gamma A plus B, something like that. And of course, if we pick, like basically, if we pick A equal to 1, B equal to 1, then this thing is doesn't have anything, right? So in that case, your map estimate, oh, okay, I mean doesn't have anything. It's if I pick A equal to 1, B equal to 1, then probably Q is just equal to 1, right? It's just a constant there. Okay, I want to be careful, like yeah, this actually sometimes will make my brain hurt because there's a several level of probability here. We are introducing a probability of a probability, right? So Q itself is a probability, but we are looking at the second level. We are looking at the distribution of that probability. Is that clear? And the distribution of this probability is because Q is a continuous random variable. So we are looking at the PDF of this Q here. What I'm saying that like the PDF of Q here will be just 1, right? But be careful not to be confused with like probability of hat is 1. It's not Q equal to 1. It's like probability of Q is equal to anything. It's just equal to that PDF is 1. Maybe let me write it more precisely. This thing, like I have like PQ, maybe I write it. The PDF here, PQ, small q here, this one is equal to 1. So if this one is equal to 1, then that's not existing, right? So the map will be just the same as maximum likelihood.
What does PQ represent?
Say that again.
What does the PQ represent? PQ.
Oh, this is a PDF.
PDF.
Yeah,
okay.
PDF of Q. Yeah. So think of like you have Q here is the probability of hat, and it can have a distribution, right? So I can have distribution. This Q here, PQ, Q here, I can have a distribution. So if this is just uniform, And my scale is not quite good here. Like Q is I can from 0 to 1, right? If it's like you just is uniform is just 1, then you don't actually have a prior in this sense, right? Then you're just multiplying a constant to this thing here. You doesn't change the setup here. So map will be the same as maximum likelihood. Now let's make it more interesting. Let's say A equal to 2 and B equal to 2. Now, what will be the optimum Q pi then, Q hat then? Oh, let me repeat this question, make it like question A, maybe like question A. Now I'm doing map now, right? I'm doing map. And let's say my prior is the Q here. So therefore like this Q here. Q, oh, maybe okay. Q, take a beta distribution, right? With the A is equal to 2 and B equal to 2, let's say, right? So now ask the same question again, like what is the optimum Q here? You sure so fast? Oh, wait. We have the same observation here. Don't forget about the observations, right? We have the observations that we observe like it shouldn't be the same way. I don't know. Oh wait. My yeah, my prior say it's not. Yeah, it's not 1 now. It's like 2 2. Yeah. Here then there's this question here like I have a different beta. It's not. Yeah. Yeah. Earlier we say that if A and B is equal to 1, then would be the same as Oh, again, let me revise write the beta distribution here. Beta Q AB is equal to Q to the A minus 1 minus Q B minus 1 over B AB here. Actually, oftentimes you don't need to care too much about this normalization factor. It's good to know. I mean, if you know this is actually is gamma, I don't always remember also. It's gamma A, gamma B over gamma A plus B. That's good to know. And of course, like for gamma function, it's good to know that like gamma x is equal to x minus 1 gamma x minus 1. So it's like it's It's actually something very good to know. It's even it's better to know the original definition. That's the integral. I usually don't remember that, but this is very useful. Yeah. But I mean, for this question, I don't think you need to go to the do any derivation here. So you guys are working on that. Is the question clear?
So in here, PQ of Q, that is equals to beta distribution, Q to the power A minus 1 into 1 minus Q to the power B minus 1.
For this particular question, like A and B is equal to 2 and 2. Yeah.
Yes.
So, yeah.
So for MAP equation, the one you have circled in here, that which was 1 previously, so that's now Q to the power A minus 1 into 1 minus Q to the power B minus 1.
Yes, the one circle now is now equal to beta. This one is equal to beta Q A equal to 2, B equal to 2. Yeah.
Okay.
Okay, I guess some of you have answered. Yeah, I guess several you have answered. So yes, actually, it's easier than you thought. Like maybe some of you thought. So, note that because of the conjugate pi, things become much easier, right? Because now you have basically, as I said, like you don't even need to worry about the normalization factor. You have these guys like q times 1 minus q, right? So if you multiply these together, you have q to the fifth and 1 minus q squared, right? And we derived earlier, basically, if you have like q to the, let's say, c and like 1 minus q to the d, then the maximum value for q will be just equal to optimum q will be just equal to c over c plus d, right? So then, therefore, like in this case, will be just equal 5 over 7. So is that clear? So imposing the pi in some sense will make it less extreme. So it's like some kind of like, just like in machine learning, some kind of regularization factor here. For example, like if I don't have really like 4 heads and 1 tail, but instead I have like 5 heads, then using maximum likelihood, I will just estimate that I will always get a head next time. It may be a pretty extreme estimate. So, but using map, then I will scale down this estimate a little bit. So I will just like, for example, if I hopefully I didn't confuse you, like changing this in the middle. So if I have 5 heads here, using maximum likelihood, I will estimate like probability of getting a head will be just equal to 1, right? But on the other hand, if I use a map here with the same a equal to 2, b equal to 2, then my estimate will be equal to what? Equal to, sorry, 6 over 7, right? So it would be like something like will be equal to 5 plus 1 over 5 plus 2 or something like. So 6 over 7, so it's a little bit less extreme, basically.
I have a question.
Yes.
So in this case, the beta 2 didn't change the maximum. Is that always the case? Can you always ignore the beta function?
Wait. Actually, it changed the maximum. It changed. For example, like sorry, let me go back to the example here. So let me don't change the value. Go back to 4 head and 1 tail. So if I have, so okay, basically, if I have 4 head and 1 tail, what? Let me just say, put this A and B here, right? I don't give an exact value, but A and B is some values here. Then I will get basically Q to the 4 plus A minus 1 and 1 minus Q 1 plus B minus 1, right? So and the maximum value of Q for this expression here will be just equal to 4 plus A minus 1 over 4 plus A minus 1 plus 1 plus B minus 1. Okay, yeah. So therefore, it would depends on or like make it a little bit like a fee.
I'm talking about the dividing by the beta AB.
You mean this BAB here?
Yes. Yeah.
It will change as well, but I'm not using this information really. This normalization factor will change with your prior here. If you change AB, this value will change, right? Because it's a function of A and B. But I mean, okay, we are ignoring that. Okay, maybe your question is why we are ignoring that, because we are optimizing Q and this BAB does not depend on Q, right? So I actually, yeah. I guess I am sorry.
That makes sense. Yeah.
Yeah, I can't confuse some of you guys. I have the BAB, but I pull it out already. I don't care because it does not depend on Q. Yeah. Yeah, good to bring it out. So let's see. Okay, and I guess next thing, let's play a little bit more on the beta distribution. So maybe I will have a new page again. I have beta again. Let me write beta q with parameter ab is equal to q a minus 1b minus 1 minus q b minus 1 over BAB, right? And again, a BAB is equal to gamma A, gamma B, gamma A plus B. And it's good to know that gamma A is equal to A minus 1 times gamma A minus 1. Now, so, and trust me, like, most of the time you don't need to do integration, like playing with this guy. For example, like if I try to find the expectation of Q, let's say, expectation of Q here, such that Q is a beta of A and B, right? Then, okay, I know that this, of course, this is an integration, right? Should be equal to Q, and then the beta distribution, beta Q AB, right? DQ, right? That's the value, right? Yeah, and then of course I can write this down. This as Q A minus 1, 1 minus Q B minus 1, B A B. This times Q DQ 0, 1, and this is equal to Q to the A 1 minus Q B minus 1 B A B DQ. So by this time now, you should stop not trying to solve this integration. I mean, like, this is the very convenient trick. Like, when you play with that, like, of course, sometimes you can look for tables, but sometimes, if you don't have an internet, and sometimes you're not even sure the Wikipedia is correct or not, you can just spend like 2 minutes and like just compare yourself. That's very easy. So, for example, like for this thing here. Now, what I need to know next is I know this is a probability distribution, right? Beta is a probability distribution. Therefore, I should have something like this beta QAB. If I integrate over 0 to 1, I better get 1, right? I should normalize to 1. So that means that like I have actually QA minus 1 minus QB minus 1 over BAB is integrate this thing will be equal to 1, or I can think of like integrating this thing, is equal to BAB, right? And I can use this, it's very convenient. So, and then I look at this now. So then what does that mean? That means that like I have this guy here. Therefore, it should integrate into B A plus 1 B, right? Over B A B, right? And then I know this is just gamma function. So this is gamma A plus 1 gamma B over gamma A plus 1 plus B, and divided by gamma A, gamma B, and gamma A plus B, right? Then I have this gamma B got cancelled, and then gamma A plus 1, I know that gamma A plus 1 is gamma A times A, right? I have this here, it's equal to gamma A times A, and I have gamma A plus B here, and I know gamma A plus B plus 1 is equal to gamma equal to A plus B times gamma A plus B and gamma A. So I can cancel all these gammas. So therefore, it's just equal to A over A plus B. So is that clear?
Can you repeat from this last integration step? Where you get this beta a plus 1? Yeah, from here, yes.
From here. Oh, okay. From here, basically, I'm using. Okay, I'm just using the fact that like this is a actually this kind of trick is not just used in beta distribution. It used for many distributions. They always have some normalization factor, fancy normalization factors. Oftentimes you don't need to actually do the integral, but you know things will be normalized to 1. So then you can take advantage of that. So I have this beta distribution here like this way. I know that like this integrate will integrate to 1, right? If I integrate from 0 to 1, I will get 1 here. So then I can rearrange the term. Then basically I have like d q1 minus q a minus 1, and this is like to the power b minus 1 is equal to bab, right? So now then you see like from here, I multiply by q, I just absorb this q into this q a minus 1, right? So then this guy here, the only difference from this guy is I just have a from a minus 1 become a, right? So therefore, if I integrate this thing here, the numerator here, I will get b a plus 1b, right? Is it clear now?
Yes, so this this fraction of 2 betas is converted into gammas, right?
Oh yes, and the b, this beta, yeah, I forgot what's the name of. I guess it's beta function or whatever. So this b function is like basically it's like actually gamma. It's like just defined by something like that. So then I basically this is I just write it as gamma, and this guy write another set of gammas, right? Then I can cancel some b's here. And the very nice property of gamma is like all you guys should remember is like gamma a is equal to a minus 1 times gamma a minus 1. So it's like gamma function is very similar to like a factorial function. Actually, gamma x is really equal to x minus 1 factorial. Yeah. When x is an integer. Yeah. So it's like gamma function is really a generalization of the factorial function. So and yeah, and using this property, I can just say gamma a plus 1 is equal to a times gamma, right? And then gamma a plus b plus 1 is equal to gamma a plus b times a plus b, right? Then I can cancel all things out, and then I will just get a over a plus b. Yeah. So it's clear now, or now, yeah. Any other questions? By the way, if we go back like the early slide here, the previous drawing here, when we have the map here, another way to think of this second question here is basically you start with the prior here. If a equal to 2 and b equal to 2, right? Now you make some observation, and given the new knowledge from the observation, the resulting this thing here, actually you look at the resulting thing here, the posterior probability. By the way, this posterior probability should also a beta function, right? Because it still have a form like this, right? Q to the oh, actually one thing like maybe I want to mention here is like, of course, this posterior probability is like PQ given your observation that basically head, tail, right? Now, what's this thing? Actually, what's this thing? It looks complicated to to compute at the beginning, right? No, no, not the maximum likelihood. Let's say about the map. So map in the sense that we see the observation, and now we're trying to estimate the parameter Q here. And for the map, it's like we look at that and trying to maximize that, right? So, by the way I'm writing here is not exact because this is proportional to this here. I'm writing this guy is actually equal to the probability of the observation times probability of Q here, and this is the observation. So sorry, probably the likelihood here is the probability of Q given the observation here. So the one I'm writing here is like the joint probability Q observation. But in the sense they are proportional, they only different by like the probability of observation, right? So I mean, this guy here is just equal to the probability of Q given observation times the probability of observation here. And of course, by definition, I'm supposed to optimize this guy right, for maximum posterior. But let me write on the other side here. But on the other hand, because I'm optimizing over Q here, so therefore like this is just a constant with respect to Q, then I don't care. It will be the same as the joint probability, maximizing the joint probability here. But what I'm saying is the posterior, after all, I'm interested in this posterior probability, right? Given the observations here, and given the posterior, given the prior is basically A equal to 2, B equal to 2, what's the posterior probability here, by the way? This posterior probability is a beta, right? Because my prior here has a form, basically, it's a beta, it's like Q to the A minus 1 and 1 minus Q, B minus 1, something like that, right? And after multiply that, it's still like Q of some form, right? So it's like still Q to the something like alpha or like 1 minus Q times beta or like something like that, right? It still like have a form like this, right? So it still have to be a beta distribution. I have a feeling I get some people lost. Maybe I don't know. I pause a little bit, make a Q9 or something like. What is PQ given T? What's that precisely? I guess I'm running out of time anyway. So should I continue or like well, I don't know. Maybe not a good idea. Okay, I can put it in the homework assignment actually. Yeah, I probably will put I ran a little bit slower than I expected, so I guess some of the question I probably won't be covered yet, but I will put the link of the slides that I have the materials, so you guys can look at that. How about the normalization factor? Conjugate, like, yes. Maybe okay. Let me just finish. Don't think of it as a question. So know that this is only a probability of the Q here, right? So it's only a distribution of Q, and you already know like the form there, the shape there, like as Kanji mentioned here. I know the form is basically yes. Is the normalization, and what is that exactly? What you written down is simply the beta, right? So it's actually for this one, you start with like prior with like parameter A and B here, and you observe like 4 heads and 1 tail. What you get is actually just the posterior probability. It's just a beta. I'm sorry, I maybe take 1-2 more minutes just get this finished. Maybe it's just a beta of Q with your parameter change to A plus 4 and B plus 1, right? Super simple. So in the sense, it's like if you start with your priors A and B is like this, and then like if you have basically like have n head observation of head and then n tail observation of tail, then your new posterior, this is the posterior probability is just equal to the beta Q A plus n hat observe n hat and observe n tails. It's just like that. Very simple, super simple. Now I talk about maximum likelihood map, like maybe I just quickly say like what will be the Bayesian estimate supposed to be like for Q in this case. So the Bayesian estimate won't be the maximum, right? In this sense, we're trying to get the maximum here. The Bayesian estimate will be like, I know the posterior is like that, right? So I know, for example, like if my A is given like, start with like my prior is like 1 head. Sorry, I'm not sure what I'm saying. My prior say I have like the prior parameters is A and B here. And I observe like n head and n tails, right? And I know the posterior probability will have a beta like this form now. Then my Bayesian estimate will be the weighted sum for all the possibility of Q. So the weighted sum of all possibility of Q will be like the expectation of Q, right? That's actually essentially just equal to this way. Beta Q A plus NH B plus NH, right? N tails. But this is nothing, it's just the expectation, right? It's just the expectation of Q here. And I guess we compute that the expectation of Q for beta is just equal to A just equal to the parameter A over A plus B, right? But in this case, A is equal to A plus NH and B is equal to B plus N tail. So therefore the Bayesian estimate will be like A plus NH over A plus NH plus B plus N tail. And in contrast, the map estimate for this guy, if you remember, for this distribution, if I have like for the map estimate, for this distribution here, it has some form like Q to the A plus NH minus 1 and 1 minus Q B plus NH, N tail minus 1, right? And you remember the maximum for this guy is actually this over like sum of this. So it's like A plus NH minus 1 over A plus NH plus B plus N tail minus 2, something like that. So this will be the map estimate of Q, and this will be the Bayesian estimate, basically. So next time I will just quickly review this back because I go pretty quickly at the end, but I guess I really will stop here. So You guys have any question, let me know. I will put kind of like some questions that related to this. So but it's okay. I probably like we have class next week. Yes, we have class. Oh, wait a sec. I have no idea. I didn't take it. Okay, I didn't take into account. So is that Thanksgiving or something? I didn't really think of. Okay, whoops. Is that a? I didn't check Canada. Okay. I don't think I should give class on Thanksgiving if they say that. Let me check Canada. Just I'm okay either way, but I guess I just don't want to do things that like is not aligned with the university. Okay, let's see. Yeah, Thanksgiving vacation is 25th to 29th. Yeah, I guess probably I won't. Yeah, then I guess I okay. I probably will only have one more class left then, because I don't think I will have time to give class during this what do you call that, the week of like preparation, my exam preparation, something like that. So I don't intend to give a class that week, but yeah, that week, yeah, I'm not going to give class on that week. But you guys are feel free to contact me if you have any questions about projects and so on. So then, okay, I actually only have one class left. Then I probably won't go that far. Then, like really, I guess I will see like what I can do. So yeah, but I was your homework will still due. Oh yeah, shoot. Is that bad idea to homework due like maybe I make it homework due like December 1st or something like that. I don't know, or like maybe November 30th. The problem is that you guys always submit late homework assignment. So I mean, if I cannot talk about solution until all of you guys kind of like complete the homework basically. So if you can like finish it by like December 1st, then I can settle that like December 1st or something like that. So then because you may be interested to look at the solution like for the last class, or maybe it doesn't matter. Maybe maybe either way it doesn't matter. Like I would just like put up the solution like eventually. Maybe that will work as well. So in case anyone is interested, yeah, I guess that probably is good. So because I probably we have so limited time, then we probably don't want to spend too much time talking about homework anyway. So okay, then I probably will set homework due like December 1st, and then yeah, and it probably will cover like some of the stuff a bit beyond like what you may need to do some reading to. But maybe you don't need to if you understand everything I talk about just now, but maybe you don't because it's a wash. It was a wash, but yeah. So, but I will put the link there if you need that you can read it yourself and so on. So I guess I will just stop here unless anyone have questions. So I will see you guys like December 2nd then. Yeah. Okay. Thank you. Yeah, you too. Have a nice holiday, Thanksgiving. All right.